Ladies and gentlemen, in the presence of Professors Heisenberg and Dirac, whom I can see, and possibly of other theoreticians whom I cannot see, I shall not be so rash as to make any statements about the theory of electrons, even in the past. But I shall confine what I have to say to the experimental side and only mention such comparatively mundane pieces of theory as would have seemed natural to those experimentalists who are engaged in the work at the time. Also, the limitations of time and, indeed, the patience of an audience require me to leave out much. And I hope you will forgive me if I devote a somewhat disproportionate amount of time to those matters of which I happen to have special knowledge. First, as to the meaning of the word. It is well known that the electron was named before it was discovered. Johnstone Stoney, an Irish physicist, and perhaps it is typical of his country that he should name something which did not yet exist, so to speak, introduced the word. He used it in 1894, and I think earlier. But what did he mean by it, and what do we mean by it now? This is not a mere matter of scientific pedantry, for in fact the electron, now for nearly 70 years, has stood for the fusion of two quite distinct ideas. And a failure to realize this has led to some unnecessary controversy which had better have been avoided. The two separate ideas are first Johnstone Stoney's, which was the idea of a natural unit of electric charge. The second, the idea of a common constituent of all forms of matter, at any rate of matter in the ordinary state, not merely of conductors. I will start with the first. It seems to us perfectly obvious, at least to those of us who have studied the laws of Faraday on electrolysis, that these laws imply the existence of a natural unit of charge, an atom of electricity. But it did not do so to Faraday himself, nor even to Maxwell some 40 years later. If I may, I will read you a quotation from Faraday. According to it, that is the theory of unit charge, the equivalent weights of bodies are simply those quantities of them which contain equal quantities of electricity or have naturally equal electric powers. Or, if we accept the atomic theory or phraseology, then the atoms of bodies which are equivalents to each other in their ordinary chemical action have equal quantities of electricity naturally associated with them. But I must confess I am very jealous of the term atom. For although it is very easy to talk of atoms, it is very difficult to form a clear idea of their nature, especially when compound bodies are under consideration. You see, Faraday, though very well aware, as he must have been, of the possibilities, deliberately rather shies away from the idea. Maxwell, in 1873, in his treatise, was even more opposed. Suppose, however, he says, that we simply assert the fact of the constant value of the molecular charge, and that we call this constant molecular charge, for convenience in description, the molecule of electricity. This phrase, gross as it is, and out of harmony with the rest of this treatise, will enable us at best to state clearly what is known about electrolysis and to appreciate the outstanding difficulties. It is extremely improbable, however, that when we come to understand the true nature of electrolysis, we shall retain in any form the theory of molecular charges. For then we shall have obtained a secure basis on which to form a true theory of electric currents, and so become independent of these provisional theories. The explanation for what seems to us such a curious attitude is that in those days the emphasis, particularly among those workers, was on the medium, the dielectric, as they called it, which included the vacuum, but the vacuum was still a thing very difficult to obtain and of uncertain properties. Nobody was quite sure whether a vacuum should be regarded as a perfect insulator or a perfect conductor. Maxwell, for example, said, according to this theory, that is the theory of his treatise, all charge is the residual effect of the polarization of the dielectric. Perhaps we are coming back to this point of view, for after all, Professor Dirac had the courage to speak openly of an ether, which for a long time was in physics a very dirty word. Helmholtz, I think, was the first to put clearly what we should describe as the natural deduction from the laws of Faraday. He said, if we accept the hypothesis that the elementary substances are composed of atoms, we cannot avoid concluding that electricity also, positive as well as negative, is divided into definite elementary portions which behave like atoms of electricity. A clear statement of what I should describe as the first property of the electron, but not proved. Now comes the turn of the second idea. It is possible, perhaps, to find a trace of it among the Greeks, but for practical purposes, we can jump to the study of cathode rays and not lose much. The cathode rays were discovered by Plücker in 1859, and Goldstein shortly after named them. For the benefit of any non-physicists in my audience, I may say that cathode rays are the earliest known form of the thing, I can only call it the thing, that works a television screen. They are formed when an electric current goes through air or any other gas at a pressure of less than about 1 part in 10,000 of the normal atmosphere. Under favorable conditions, they can be seen as luminous streaks in the gas coming from the negative terminal, which is called the cathode, hence their name. They were studied, however, in the early days, indeed now, mostly by the fluorescence they cause when they hit the walls of this highly exhausted tube, when they hit the glass. But to make the fluorescence stronger, it is preferably covered by some strongly fluorescent substance, just as is the modern television tube. It was early discovered that these cathode rays were easily deflected by a magnet, that they behaved like a flexible current, and they were deflected in the same way as would be a flexible wire carrying a positive current into the cathode, or, comes to the same thing, a negative current out. Goldstein proved that if an obstacle were put in their way in the tube, it would cast a shadow at the end of the tube as if the rays were emitted normally through the circuit, like that. Imagine this, a discharge tube, here's a cathode, we can bother up the anode too much, and cathode rays are coming out from this. You put an obstacle in the way, and you find we've cast a shadow, and the black bit is strictly limited by the lines drawn normal to the cathode and passing through the obstacle. You cannot see round the corners of the obstacle to the cathode as you could if it was a question of the ordinary emission of light from a red-hot surface. Goldstein thought that cathode rays were waves in the ether. Crookes, on the other hand, Sir William Crookes, who studied them in England, thought them particles, and was followed in this view by most English and French physicists. In fact, as we now know, both sides were right. An idea, I think, on which they would have united in regarding as quite ridiculous. In 1895, Perrin, the French physicist, proved that if the cathode rays are caught in a metal cup, as in a trap, it acquired a negative charge. Hertz, however, as early as 1883, had found that the cathode rays were, he thought, not deflected by an electric field, and even more curious, that they did not appear to exert a reaction on a magnet which deflected them. Both these are almost impossible to reconcile with the rays being moving charged particles. Hertz also found that these rays could go through very thin films of gold. This led to an important series of experiments by Professor Lenard, Hertz's pupil, who made brilliant use of this discovery. Using very thin windows of this kind of gold or some other things, he got the cathode rays right out of the tube into the atmosphere and studied their properties, in particular their absorption by many different substances. A variant was to send them through the end of the tube into another glass vessel, which could be exhausted, so that their passage in gases at a very low pressure could be examined. The rays can go a long distance in a near vacuum. I think Lenard sent them up 2 or 3 meters. He found that the absorption depended only on the mass per unit area of the absorber and appeared to be quite independent of its chemical character or of its physical state. The magnetic deflection did not depend on the gas through which the rays were going, but did depend on the voltage of the discharge which made them. He did not try changing the gas in which the rays were made. At the end of his experiments, he remained convinced that the rays were a wave phenomenon in the ether. Now, if the waves are particles, it ought to be possible to find the mass of a particle, or at least the ratio of the charge to the mass. The magnetic deflection is quite easy to measure, and this gives you the ratio of m the mass, v the velocity, and E. But this, of course, by itself is not sufficient to give you m and E. However, a number of attempts were made to guess or measure some other quantity which would enable you to do this. Schuster, in 1890, Schuster was then working in Manchester. He estimated the value of mv squared upon 2, by a series of arguments, and found, as he thought, limits between which it must lie, m by E must lie. Unfortunately, the limits were very wide, and they just permitted a ratio corresponding to the mass of an atom, or rather the ratio of that to the charge carried by an atom in electrolysis. Schuster concluded that the cathode rays were probably charged atoms. But when Lenard's results came along, and perhaps its results of the transparency, this was very difficult, at least to people of those days, to accept. I think it is of interest to consider what the evidence in 1896, the end of 1896, and to see how the battle stood between the two sides. In favor of particles was Perrin's experiment. Obvious, you have particles and they go into a cup, then they would give their charge up. Simple. This was countered by saying that indeed there might well be charges about, but that they were only a more or less accidental accompaniment of the rays. Then there was the magnetic deflection, which the particle theory explained easily, the wave theory only as a special property of these waves. Possible, but not explained. Lenard's results on absorption were, in the opinion of my father, J.J. Thomson, though not in the opinion of their discoverer, evidence for particles. Absorption of waves, you see, is usually or often selective. Thus, glass is transparent, aluminium of about the same density is not. But when it comes to a question of bullets, mass becomes more and more important. Against particles was the apparent absence of electric deflection. Very strong, if really true. The fact that the rays could go through solids, which remained gas-tight after they'd been through, impressed the people of those days very much, and was probably even more than the difficulty of the absence of the electric deflection. We are now so used to such things, we're used to all sorts of particles going through quite thick bits of metal and producing no apparent effect, that it is difficult to put ourselves back and look with the eyes of 1896. Early in 1897, the first day of the year, in fact, Fischer gave a paper to the Scientific and Economic Society of Königsberg, which I think deserves more credit than it usually receives. He believed in particles, and he tried to find m by E by measuring mv over E, and not this time mv squared by 2, but V directly. He tried to time the rays over a certain distance in his apparatus by comparing this time with the time of oscillation in a Hertzian oscillatory circuit, the time that such an oscillation took to change by a quarter period. The period of the circuit was measured in a separate experiment by Alecha Bridge. In fact, in these early experiments, which I am now referring to, his circuit could not be got to give quite a short enough period, and consequently he could not get a measure, but he was able to show that the value of m by E could not be more than 1/1000th of the corresponding ratio for an atom of hydrogen in electrolysis, and was probably about 1 in 2000. The merit of the work, first, is that he proved that m by E must be much smaller than for an atom of hydrogen. Second, that he recognized, at least to some extent, the universal character of cathode rays. He's speaking of atoms of electricity, though he did not claim that the cathode rays formed part of ordinary chemical atoms. The weakness was that he did not answer the objections of those who denied the rays to be particles at all. If they were not particles, they probably would go with a speed comparable with that of light, if not equal to it, except that his presumed small mass might be associated with small size, he brings this point out, and so penetrate solids more easily. My father, J.J. Thomson, can I have this first slide, please? This shows a picture of him taken at about that period, who had been working for some time on discharge through gases, gave in May 1897 a lecture at the Royal Institution, Faraday's old home, which was printed in full in the paper called The Electrician of May the 21st. This lecture solved, in a way, the problem of m by E and made it probable that these particles were a universal constituent of matter. Firstly, he answered the objection to Perrin's experiment by showing that if the cup was not in line with the rays, as Perrin had originally arranged, Perrin simply made the rays go straight into the cup. My father put the cup down here, and so that the rays had to be bent by a magnetic field to get in, and they only gave their charge to the cup if they were bent, and you could see their path, so that they actually went in. This showed at least that the connection between the charge and the visible ray was a close one. Then he showed that the magnetic deflection of the rays, second slide please, was the same whatever the gas in the discharge tube, provided the voltage in the tube was the same. This meant that you had to have different pressures with different gases in the same tube in order to get the voltage the same. But if you adjusted it from that point, if you made the voltage come right, then the deflections were all the same. This gives a kind of apparatus he used, very simple form. Cathode is right on the right, and the cathode rays came through a hole in the opposite anode. They were then deflected from the magnetic field produced by large coils, circular coils of wire, and the path of the rays was photographed. The next slide, please. This shows the track. The curved track is when the magnetic field is on, the straight track when it is not. And measurement showed that the lower one of these is with carbon dioxide, the upper one, I think, with hydrogen. It was for the same voltage, the deflections were the same. He then explained, and this perhaps was the most important single point, Hertz's failure to find an electric deflection as being due to the neutralizing effect of the charged particles, ions, that is, produced by the rays themselves as in going through the gas. These charged particles could cluster round the plates which were intended to produce the electric field, and so prevent them from doing so. Neutralize, in fact, the charge on the plates, and so prevent it acting in the space between where the cathode rays were. By improving the vacuum, he was able to demonstrate that, in fact, the rays were electrically deflected. This removed the strongest argument against the particle theory. And as you see, it was all a matter of better vacuum technique, better pumps, in fact. I do not think that science physicists nowadays perhaps realize how much our science owes to the development of the incandescent light bulb, because this made vacuum a commercial product and enormously improved the pumps available for the purpose, although it took some time to do so. When I first began research in the Cavendish, I used a Toppler pump for evacuation. And the Toppler pump is a thing you pull up and down by hand. There's a heavy reservoir of mercury, and it is very good for the muscles of the back and very bad for the temper. However, J.J. Thomson then proceeded to measure M by E by determining mv over E as here and mv squared upon 2. He actually did it by a method which now appears to have been almost forgotten. He allowed the cathode rays to be absorbed into a capsule which contained a thermocouple, and he measured the heat. He measured simultaneously the current carried, as in Perrin's experiment, and the heat generated. This gives you, of course, the relation of the kinetic energy to the charge. He found a value about 1,000th of the value for hydrogen, as Bichette had done. But it's fair to say that J.J.'s was a measurement, though a rough one, and not merely a limit. In October of the same year, he published in the Philosophical Magazine a more detailed paper which included all that was in the lecture and one or two other things, principally the method of measuring E by M using the electrical deflection, which is now so well known in textbooks that I shall not spend time describing it. He also included an account of the possible ways in which charged particles could be arranged in an atom. The most important part of the lecture, to return to that, though perhaps not so many of the audience realized it, was that in which he claimed the cathode particle, he called it a corpuscle, as a fundamental constituent of matter. He was led to these conclusions, so he told me, by the independence of the properties of cathode rays of the chemistry of the materials involved. Didn't matter what metal you used for the cathode, didn't matter what gas you used for the discharge. In especial, he was impressed by the constancy of the magnetic deflection of the rays, however produced, to which provided the voltage was the same, to which I've just referred to, and by Lenard's experiments on absorption, which are readily explained if the absorption is due to corpuscles and the number of these is proportional only to the mass. Admittedly, this stupendous hypothesis rested on a somewhat slender foundation. Most of the facts are, as is now known, not exactly true. I do not think that this is really an objection to his conclusion. Nature has a curious habit of working, as it were, by successive approximation, and too accurate experiments can at times be a hindrance to interpretation. There was, however, one quite different result which helped and to which he referred in his lecture. Zeeman had just discovered that the light emitted by a sodium flame is altered by a magnetic field applied to the flame. Zeeman had applied to Lorentz, who at once explained it in terms of his electron theory, a theory of conduction, and deduced a value of m by E for the assumed emitting particle, which agreed reasonably well with my father's for cathode rays. Incidentally, here is another instance of limited knowledge being a blessing, for in fact the sodium-Zeeman effect is abnormal, and if known with accuracy when first discovered, would have been quite a difficult morsel for the Lorentz theory to digest. So far I have assumed, as most people in fact then did, that if there were charged particles, their charges would be closely related to, and probably equal to, that on a univalent ion in electrolysis. There was, however, extremely little evidence for this. It soon began to accumulate, but was at first indirect, and indeed, as far as I know, no one has yet measured the charge on an individual cathode ray, though they may have. The ionization produced by X-rays had been studied by J.J. and his then pupil Rutherford in a paper published the year before. Using the work of condensation of drops onto ions, which had been studied by C.T.R. Wilson, and the idea due to Thomson of measuring the mass of a drop, of a small drop of water, by the rate at which it fell through air, J.J. was able to measure the charge on an ion of X-rays, the ions of X-rays. And his result, though inaccurate, came to a value which was quite compatible with the very roughly known estimates, really rough estimates, then made as to what the charge on an ion in electrolysis would be expected to be. In 1900, Townsend, by measuring the diffusion of the ions due to X-rays, and of whose mobility had been measured, was able to prove with considerable accuracy that the ions, X-ray ions, had the same charge as the ions in electrolysis, though he did not actually measure either separately, to prove the equality. This very important result followed determinations by my father of m by E for the carriers of electricity in two other cases, namely the negative electricity admitted by a hot wire and the negative electricity given out in the photoelectric effect, that is, when light, ultraviolet light, acts upon what was a zinc plate. That is the first example discovered. He found that in both cases, the value of m by E agreed reasonably with that for cathode rays. In the latter case, by a modification of the drop theory, he showed that the charge was roughly the same as that found for X-rays, and hence by Townsend's result for the monovalent ions for electrolysis. All this added up, of course, to evidence for a natural unit of charge, which in fact everyone came to believe by, I suppose, about the time 1900. But the proof was incomplete in one respect. All the experiments that I have described only measured an average value for E, and it was were quite capable quite compatible with there being a considerable variation of this quantity about a mean. H.A. Wilson, in 1903, introduced a new idea in the measurement of charge. H.A. Wilson, not to be confused with C.T.R. Wilson. H.A. Wilson lived to a great age. In fact, he only died last year, just on 90th year. And he told me a year or so before he died that he thinks that it was Thomson who suggested this particular thing, namely the use of a vertical electric field to modify the rate of fall of a charged drop. Well, anyhow, Thomson used this, H.A. Wilson used this, and got another measurement of the charge, which agreed tolerably well with the revised version of my father's. The importance of this was in its use by Robert Millikan. Next slide, please. Millikan delivered a paper in 1909 to the British Association at the meeting of Winnipeg. It was the first scientific meeting I ever went to. I was only a schoolboy. And in this he described an improvement of H.A. Wilson's method. Wilson actually only used his electric field downwards to increase the rate of fall of his drops. Millikan used it upwards, and what was more important, he reduced the ionization, so that instead of his drops appearing, as it had been done in the case of my father's experiment and H.A. Wilson's, as a cloud, of which you could observe the top slowly sinking under gravity, Millikan had so little ionization that he could see in a microscope individual drops when strongly illuminated. And their up and down motion could be followed. Soon after, he improved the experiment by substituting oil drops for water and allowing them to gain and lose their charge by picking up ions produced in the air by a small radioactive source. This is the familiar experiment which is described in all the textbooks and which finally established the unitary character of charge. A charge is not, in fact, a question of average. All charges are integral multiples of a unit. The existence of an electron in the first sense was now fully established. I must move on rapidly. Until about 1923, the electron regarded as a small charged sphere, perhaps owing its mass to its electrical energy, or some of its mass to its electrical energy, was a fundamental concept in physics. And it is a concept which appeared to stand up pretty well to the revolutionary changes produced by special relativity and the earlier stages even of the quantum theory. However, about 1923, it became clear that the electron was more complicated. Certain things in spectroscopy, the mere simple fact that the D lines of sodium are double and not single, was a difficulty. Earlier explanations of this had proved unsatisfactory. And Goldschmidt and Uhlenbeck put forward in 1925 the idea of an electron spinning about an axis, and in virtue of its spin having a magnetic moment. This was satisfactory for a time, but it all got swept away by the flood of wave mechanics a little later. In the early 1920s, the main cloud on the face of physics was the behavior of radiation. It's well summed up in that very famous statement of the elder Bragg, that light behaves like waves on Mondays, Wednesdays, and Fridays, like particles on Tuesdays, Thursdays, and Saturdays, and like nothing at all on Sundays. At that time, about 1924, we were all thinking of possible ways of reconciling the apparently irreconcilable. One of these was supposing light to be perhaps particles after all, but particles which somehow masqueraded as waves. But no one could give any very clear idea as to how this was done. The first suggestion I ever heard, which did not stress most of all the behavior of the radiation, came from the younger Bragg, Sir Lawrence Bragg, who should have been here during these days, but unfortunately had a sharp but short attack of pneumonia, and although he's recovered from that, his doctor rightly said he must not come here much as he wished to do so. Bragg, as I was saying, once said to me that he thought the electron was not as simple as it looked. But he never seemed, I don't think he ever followed this idea up in detail. It made, however, a considerable impression on me and predisposed me to appreciate Louis de Broglie's first paper in the Phil Mag of 1924, which was virtually a summary of his thesis for the Paris doctorate. In this he suggested that all particles are associated with waves, not only radiation. I was sufficiently impressed by this actually to chance my arm and write a short theoretical paper in the Phil Mag, which I should say is probably the worst theoretical paper ever published, but I mention it merely as showing that I did take an interest in the thing at the early stage. There was some talk of this theory at a meeting of the British Association held in Oxford in August 1926, which I attended, and I then began to think about the waves as perhaps producing diffraction effects. Dr. Elsasser had published a very short note on this point before, but I had not in fact seen it, but it is possible, and I think not unlikely, that some of the people who heard talking about this and with whom I discussed it had in fact read this note. Now, at the same meeting was C.J. Davisson. Next slide, please, at the Bell Telephone Laboratory. I do not recall any conversation with him, and I don't think we met. We certainly didn't discuss this subject. His discovery of electron diffraction arose from a study of the scattering of electrons and the production of secondary electrons from metals. It was part of a more or less routine study of the behavior of electrons colliding with metals, which was of interest to a commercial firm dealing in X-ray targets and so on. The first paper on nickel with a man called Kunstmann appeared in Science of November 1921. It described some surprisingly sharp peaks of reflected electrons, which Davisson considered could be explained by scattering, classical scattering, of course, from two shells of electrons. In 1925, after studying some other metals, he came back to nickel. Up till now, the experiments had all been on ordinary polycrystalline metals, engineering metals, so to speak. But by accident, the accident of a broken liquid air trap, a specimen became oxidized, and in restoring the surface by heating, it recrystallized into a very small number of largish crystals. It became, in fact, virtually a single crystal. There was a complete alteration in the pattern of scattering, and the former theory had to be abandoned. Davisson was inclined at first to replace it by one of transparent directions, as he called them, in the lattice. But partly as a result of the visit to the BA meeting at Oxford, he came to believe that the effect was connected with the theories of de Broglie and Schrödinger. Schrödinger had by that time taken up the de Broglie theory and turned it into more conventional mathematics. This was the theory that any particle, electron, photon, or others, had essentially linked up with it wave properties, and that the relation between the wavelength and momentum was given by the famous formula that the wavelength is equal to h divided by the momentum. As a result of careful research, Davisson and Germer got the first electronic beams in positions which could be explained in this way on January the 6th, 1927. We might have the next slide, please. The slide which is coming on, that's it, is a diagrammatic picture of a of a nickel crystal with a beam of electrons coming down on it. The nickel crystal is shown as a cube with the one corner cut off, so as to expose what the crystallographers call the 111 face. The electrons are supposed to be incident on it, and what he studied was reflected beams of electrons indicated by first order, second order, first order, second order up above. This, the rest of the diagram, I haven't time to go into, shows you how the atoms in this crystal are arranged. This was known before. In fact, he got results which could be explained as diffraction by the top layer of atoms, considerably modified by the second and third layers underneath. I think we'd better have the next slide. In these slides, I'll just take these three are similar, different examples of the same thing. You see certain points plotted in which wavelength, as calculated by the de Broglie formula, is plotted against the sign of the angle. The lines are purely theoretical. There is in this no adjustable constant, you see. You have lambda, the wavelength, is h over mv, the momentum. The velocity of the electrons, or the energy of the electrons, was known from the energy applied to them, and only electrons which had retained 90% of their energy were recorded in the Faraday cylinder to which they were shot. Now, you see that the points lie quite well on the lines. The theory also indicates just where on the lines they should lie. In this respect, the agreement was not quite so good, although it was reasonable. That is to say, the right number of points existed in the right place, in roughly the right places. But the point is that here you have a theory which is no adjustable constant, because you have waves, if they are waves, of known wavelength falling on a grating of known spacing, because the arrangement of the atoms in nickel had already been determined by X-rays. I want to stress the extraordinary beauty, experimental beauty of this work. Davisson used electrons of the order of, 143 volts, 65 volts, 54 volts, quite slow electrons. These are very difficult things to control, and the work required a degree of vacuum technique which even now would be considered respectable, and in those days was absolutely outstanding. It was one of the most difficult experiments, I should say, that has ever been successfully done. And it proved clearly that de Broglie's ideas were, at any rate, in some sense, right. Davisson's results were first published in a letter to Nature in April 1927. Very shortly, I think a matter of a few days after the Oxford meeting, I was visiting at the Cavendish, although I was then actually working professor in Aberdeen. I saw some experiments on the scattering of electrons in helium, and these showed certain effects, particularly certain directions of strong emission, which recalled to me the halos one got in an experiment which I had done as a student, and which goes back to the time of Young, who called it an areometer. I won't do the details, but you get halos, rather like the halos you can get around the sun or the moon. I remember feeling this is obviously what it is. And I was very annoyed that I hadn't seen the thing, nice for myself. But I said, well, it's been done with gas, helium, I'll try it with a solid. The moment I went back, I tried to do it. Now, the curious thing is that it turned out that the experiments I actually saw, though they were proved later, were fallacious. They were experimental. You can, in fact, get effects like these, but these ones I actually saw were not right. So I shall not mention the name of the experimenter. So I asked a young research student named Alexander Reed to look at the problem, using a thin film of cellulose acetate, actually. The next slide, please. This shows the apparatus in which A is a discharge tube, and the cathode rays coming from extreme right go through a fine tube at B, then through the celluloid or other specimen at C. They then hit against a fluorescent screen at E. And to make the effect permanent, you can lower a photographic plate at D so that it comes in front of the screen, and then the actual impact, of course, of the rays on the photographic plate makes it developable. Actually, the experiment, this is the apparatus I used a little later, but the experiment was an easy one to do because it so happened that we've been working on the scattering of protons just before. Practically all one had to do was to reverse the polarity of the induction coil. Almost at once, Reed got photographs which had rings round them, on them, and looking very much like the sort of rings you get in the Young's areometer experiment. I was a little skeptical at first, as we'd had photographs of scattered positive rays, which had shown apparently sharp edges, which on examination turned out to be only contrast effects. However, the photometer showed the reality of the electronic halos. They were what one might expect from a collection of molecules of definite size orientated at random, and the diameter varied with the energy of the electrons in the way to be expected on de Broglie's formula. The size was also about what one would expect for a long-chain carbon compound, but that was only rough. Next slide, please. This shows the best we ever got. It's much the sharpest ring we ever got, so much so that I think the thing must have recrystallized somehow. The others were much fuzzier and less suitable for reproduction, but perfectly possible to measure. We published a note in Nature under our joint names in June 1927, 2 or 3 months after Davisson and Germer's first publication. Well, the structure of celluloid was then unknown, and for a proper test, it was necessary to use diffraction by a known crystal lattice. Metals suggested themselves. They were well known and reasonably easy to work. But this was before the techniques of spluttering and evaporation for making very thin films had been developed, or at least before I knew them. The films which I used, this time working by myself, were of gold, aluminium, and platinum, and were prepared by the chief mechanic of the workshop, the late Mr. C.G. Fraser, to whom the success of the experiment is entirely due, because this is the one difficult part. He was a mechanic of the old school. He had been trained as a watchmaker, and he got the astonishing gift of being able to produce a complicated and perfectly working piece of apparatus after one had just scribbled something on some dirty pieces of paper lying on his workshop bench. Those of you who've had the immense good fortune to work with such a man will realize, I'm not exaggerating when I say that whatever may be the value of wives, good mechanics rate far above rubies. Well, the first films we tested were of gold and at once gave rings which agreed quantitatively and qualitatively with the theoretical expectation for the diffraction by a face-centered cubic lattice of side 4.06 angstroms, which was the accepted value for gold. In fact, they looked exactly like what you would get with X-rays, except for scale. I would like the next slide, please. This shows two of the earliest ones we got. The rings are very fuzzy because of bad technique, but they were the earliest ones. And you see that these are two pictures varying only in the energy of the rays. The energy was measured by a spark gap, and you see that the one with a 10 millimeter spark gap, the inner ring, which you can easily see at any rate, is considerably larger than the inner ring where there was 20 millimeter spark gap, roughly speaking, in the proportion of the square root of 2. And this is what you would expect, because the size of the rings goes as proportional to the wavelength, and according to the de Broglie formula, the wavelength diminishes as the square root of the energy increases. Well, I might say that, we'll have the next slide, please. One shows some of aluminium. These corresponding things with aluminium. The aluminium we had was the film of aluminium. The crystals were quite large, so that instead of giving continuous rings, as you would expect with an infinite number of crystals present, because each crystal only gives one little point on the ring, you see definite dots. But these dots are arranged on rings in the same way. And you see, again, position of the dots, take those ones on the horizontal, where the energy is low, the size, distance apart is greater. Actually, measurement of a number of pictures, which were in fact, much better than these. I've shown these because they were among the very earliest, but we got much better technique and could measure them quite sharply. And they agreed in absolutely every respect with what de Broglie's theory would indicate. The rings were all of the right size, both in relative size as agreeing with the structure of the metal and in absolute size as calculated from de Broglie's formula. I published a note in Nature in December 1927 on the platinum ones, and the Royal Society paper on the experiments with gold and aluminium appeared in February 1928. That is to say, 2 or 3 months later than Davisson and Germer's paper, which appeared in the main paper, which appeared in the Physical Review late in 1927. The objection was raised to these experiments that they might in some way, though the people who raised the objection did not explain how, be connected with the production of bremsstrahlung, that is to say, X-rays, by the collision of the electrons with the foils. I was, however, able to disprove this in a second paper by deflecting the electrons after they had passed through the foils by a magnetic field, and showing that the rings and the center spot, which is due to undeflected electrons, were equally deflected by the magnetic field. Most of the electrons forming the undeflected spot, as we call it, were electrons which had actually passed through holes in the film, because all these films had considerable holes, besides in their thin areas. So that whatever it was that formed the rings was deflected just like the original electrons, and therefore presumably electrons are certainly not X-rays. Later, showing the theory of scattering developed by Born and by Mott, I was able to show that an equally good agreement held for the relative intensities of the rings formed by a gold specimen. With this approximation, the wave properties of the electrons had now been established in the sense that electrons, if numerous, are detected where the Schrödinger waves are strong and in numbers proportional to the square of the wave function psi. This statement is incomplete, just as was the point electron before Gauss-Schmidt and Uhlenbeck, and for a similar reason. It required the genius of Dirac to make the necessary theory. In most experiments with free electrons, the actual change in the predictions between the Dirac and the Schrödinger electron is rather small, but it has been detected and the Dirac theory confirmed. Well, gentlemen, this brings one roughly up to the end of, I think, the experimental work which could fairly be said to relate to the discovery of the electron, as contrasted with the immense amount of work which has been done on the properties of electrons in and out of atoms. And so here I bring my lecture to its close.